In this video I'm looking at the transmit side of this G4DDK anglian 3 transverter. First I look at the intermodulation by a two-tone test. I have two signals, one at 28.1 and another at 28.2, both at the level of 0 dBm. They are combined in a hybrid, a 3-port hybrid, where the third port just has a dummy load. The output here is attenuated by 5 dB. That's a factor of 3. And then it goes through these attenuators, which are set to 21 dB. Means minus 26 dB M into this box, which means that the peak power is minus 20 dBm. At that point, the output power is the nominal power that this unit is set for, and that is 18 dBm. So each tone now is 12 dBm, and intermodulation is down by a little bit more than 50 decibels for the third order product, and the fifth order is about 70. So this looks good. Any amplifier that comes after is going to be more non-linear than this. I can attenuate now by 3 dB, and you can see that the third order goes down to minus 60. So this looks all normal. Another 3 dB, and we lose another 9 dB on the third order intermodulation. So far, so good. And I have restored the signal level, and I will check it with the spectrum analyzer. And when looking at 28 megahertz, the expected signal level, 26 dBm, is just what I'm seeing here. I don't have a low noise oscillator for 28 megahertz, but I have one for 14.15, and I have connected it in parallel to two of the inputs of this box here, and inside is a 23 dBm Schottky mixer. The output contains the difference frequency, which is 0, means a DC voltage, and the sum frequency, which means the double, which is 28.3. And then I go through this attenuator again, and up to the spectrum analyzer, and I have set the level to minus 20 dBm. 19.8. As very much expected, I see a single carrier on 144 at a level of plus 18 dBm. The output is now connected to these attenuators, set to, what is it, 28 dB. And then the signal goes into my WSE converter chain. And this is what I see on the screen. The saturation is just a quarter of a dB above this signal level. And here is, and I have calibrated the S meter to show 0 on the signal. And I move 5 kilohertz downwards from here. That is 314. Well, that's here. And the bandwidth is 1 kilohertz. And I can read the noise floor in 1 kilohertz to, well, I had to wait, minus 94.5. And then 10 kilohertz away, it will be here, the noise floor is very much the same. And then another 10 kilohertz down to come to 20 kilohertz. And the noise floor is very similar. So this looks a little bit odd. The noise floor at 20 kilohertz on the transmit side is minus 96.2. I now attenuate the signal. Well, I click on the signal first here, and we can see 0, and I attenuate by 10 dB. And what happens to the noise floor? It goes down by nearly 10 dB also. So this looks like wideband reciprocal mixing, and it's different from what I have seen in the receiver test. Just to make sure, I have taken this same signal and routed it into my Perseus, and this is what I see. And let's say 10 kilohertz away, we are now at 317, so I want 327. Well, somewhere in between. And here you can see the noise floor is minus 117 or something. So the noise floor, I can see from the anglian transverter, really originates in the transverter and not in the 28 megahertz signal. I have set the output again to plus 20 dBm to read 0 on the S meter, and I disconnect the 28 megahertz signal on the far side of the attenuator for the transverter to still see 50 ohms. And here I can see the noise floor from the anglian with the dummy load on the 28 megahertz input. It's minus 110, so it's a good bit below the noise I see when the carrier is on. And now I can disconnect the cable from the anglian output to the receiver attenuator. And you can see the noise floor of the WSE is about 5 dB below. So the noise I see is really reciprocal mixing of some kind. I think it is AM noise, because if it were phase noise from the local oscillator, I should see the same on the receiver, but on the receiver it looks a little bit different. I will now do a couple of experiments. I have set the frequency to 144.310, and I expanded the dB scale so I can read directly from it. Now the level is minus 94.5. One possible source of AM noise is this IC7. If there is audio noise, low frequency noise on pin 4, that could cause modulation. So I have tried to put an inductor. It happens to be 6.8 nanohenry, but that's not critical at all, in series with a 10 microfarads tantalum capacitor to make the low frequency noise on the input pin very low. And indeed, this actually made a difference. The noise is now 3.5 dB lower, and not so far away from the minus 102 I was seeing in the receive mode. So there is some more noise source, and I will see if I can find it. There is one more of these amplifiers, SPF 5043, right at the transmit input. This resistor is not mounted, so it is giving gain. I have decoupled this one also for audio frequencies, just like the other one, but the inductors, both this one that I said was 6.8 nano Henry, it is 6.8 microhenries, of course, so it is a high impedance for RF, and this one is the same, 6.8 microhenries and 10 microfarads. This second decoupling also made a significant difference. The noise is now minus 102, that's minus 132 dBc per hertz, and that's actually the same that I saw on the receive side. But I start to suspect that also the receive side suffers from AM noise. So I will continue and look at the further possibilities of decoupling amplifiers. There is one more of these sideband noise modulating devices, and it's in the oscillator. And I have decoupled that one also the same way, 6.8 microhenry and 10 microfarads. It doesn't make much difference, but it makes a dB or so. The reason is that the mixer is not transferring the amplitude of the LO. The signal level on the LO the output signal is not proportional to the LO signal because the mixer is partly saturated or maybe fully saturated. But even so, a small improvement. And note, this is AM noise. You wouldn't see it on a standard phase noise setup. Everybody is always thinking that noise sidebands is due to phase noise, but that's not correct at all. It's very often so that we have amplitude modulation due to phenomena of the type you have seen in this video. I will measure the sideband noise again with this modified transmit side of the anglian transverter. The carrier is at 0, of course, and the frequency is, if I read on this upper scale, 319, so I wanted 314. What? 314 here, and I have to do something to the scale. Sorry. And here we have the 5 kilohertz reading, minus 102.6. And then 10 kilohertz means 309. Should be somewhere here. And the noise 4 is just a little lower, minus 104. And then 20 kilohertz away, that would be 299. That's a little bit too close to the center discontinuity, perhaps. I look at a little bit closer and a little bit closer and a little bit further out, and look for the average, and that's 105, and I don't measure that carefully. And then I click on the signal again here, and then I step 50 kilohertz away, like that. And then the noise floor is minus 106. And 50 more. This is at the 100 kilohertz separation. I can see the noise floor at minus 108. And now I switch off the 28 megahertz signal. And very little happens to the noise floor, so it is no longer dominated by reciprocal mixing. So here are the final results of the modified transmit side on the anglian transverter. The improvement of these decouplers together is about 10 decibels at 10 kilohertz. I have tried to decouple the remaining possible sources of AM noise. That means the input pin of this amplifier here, and it makes no difference. Also, the base on this transistor should be decoupled for audio frequencies, but it doesn't make any difference. That's because there is current feedback from this resistor. Current feedback from this resistor makes decoupling here not needed. And it's the same with this transistor. It has a kilo ohm in the base, so it is not so sensitive for small voltage variations on the base that will not change the currents because of the current feedback. But there are some things to do on the receive side, but that's not in this video.